So in particular, if you look at the way multi-class classification works in machine learning, typically it's order k. So if you're choosing amongst k different things, you have an order k computation to do. And that's odd, because information theoretically, you only need an order log k operation, right? So you only need to specify log k bits in order to specify what you're trying to predict. So there's an exponential gap between k and log k. So this is the ratio of k over log k here. It's a big ratio. It's approximately linear. And now there's a question of why are people using algorithms that are exponentially slow, right? I mean, why do we use multi-class algorithms that are exponentially slow? Okay, so we need to discuss this. There's several ideas people have for how to address computational complexity. One of them is, maybe in all of the multi-class problems we care about, there's some pre-existing hierarchy. And that's often true. There is some sort of hierarchy that people have. Like, for example, ImageNet is a good example. Let me go back up a little bit. Right, so ImageNet is a big vision data set, which is about here in terms of the number of classes. But more generally, you could think of search, which would be about there in terms of the number of classes, right? So anytime you're choosing amongst a very large set of things, you might, maybe this should actually be thought of as a multi-class prediction problem. I'm thinking about both the training time and the prediction time. Both of those are important. And okay, so I think the distinction becomes a little bit important sometimes when you're looking at things that people have done. Sometimes people create, they have an order k training time to create an order log k evaluation time. And that's okay when k is not too large. But when k becomes larger, then your training time had better be order log k as well. Right? So in the end, you need order log k for both. Okay, so sometimes you have a pre-existing hierarchy, and that's nice. Sometimes you're doing structured prediction. So you're thinking about doing part of speech tagging, and you can think of the sequence of tags for each of the individual words in your sentence as one very complex label, right? That's sort of another version of a pre-existing hierarchy. And then, of course, there's decision trees. Decision trees are naturally logarithmic time. Okay, now, somehow these aren't adequate. And one way to look at this and say that it's not adequate is when you think about really big scale problems like search, it's not actually a decision tree which is being used to figure out what to get displayed. To a first order approximation, there's some sort of keyword matching inverted index which does things. There's machine learning which comes in all over the place around the sides, but it's really the inverted index which is pulling up the results that the machine learning gets applied to at relatively small scale. So, so what is going wrong here? So if you have a pre-existing hierarchy, okay, so now there's a question of, are you a machine learning person or not, right? Because if you're a machine learning person, then you would like to not actually use a pre-existing hierarchy. You'd like to be able to infer a hierarchy, and maybe you could actually infer a hierarchy which is better than something that somebody engineered, right? That would be nice. Structured prediction is nice, but maybe you don't actually know how to structure things. Maybe there is no natural parse order. Like imagine that you're trying to predict the components of an image, right? So people do parse images, but the order in which they parse images is rather ill-defined. And so you could try to engineer in these things, but maybe if we're real machine learning people, then we hope that, that we can actually do it better than some sort of pre-engineered type system. And then, of course, there's decision trees. And decision trees are actually pretty compelling in a lot of ways, because how else are you going to get logarithmic time? But there's something kind of funny about decision trees. Most of the implementations of decision trees don't actually deal with a large number of classes that well. Right? So most decision trees are, I mean, many of them are just for binary prediction, but some of them can deal with small k, multi-class classification. But often they kind of break down when you start going to hundreds or thousands of classes. And maybe that's partly a matter of the features, or maybe that's partly a matter of exactly what they're optimizing it internally. Okay, so SICM is a conference for knowledge engineering. These are my responses. So I've never published a paper at SICM. Maybe it's a good conference, but I want to do machine learning. I'm trying to find a machine learning solution to this kind of problem. I believe that the data should lead the way, basically, and I want to do as little engineering as possible. When you look into structured prediction, you discover that if you want to show that you're going to get good performance, you either need to show that you have access to specific models of how the world behaves, or some sort of optimal policy which can demonstrate how things behave. But in many such situations, you have neither. And now it's kind of a frustrating barrier that we're trying to get around. Okay, so again, why don't we have this exponential speedup? Okay, so hypothesis number one would be that it's not possible. And let me show you an example why you might think it's not possible. Suppose you have three classes. Suppose the probability of class 1 is 4, the probability of class 2 is 0.3, the probability of class 3 is 0.3. And then you have a decision tree of this sort where you have a 2 versus 3 node, and you have a 1 versus 2 versus 3 node. And then you use divide and conquer, right? So we say, is the label 1 or is it 2 or 3? And now we ask, what happens to the optimal predictor here, right? So the probability of 1 is 0.4, and the probability of 2 or 3 is 0.6. And that means the optimal predictor will choose 2 or 3. And that says that you lose. Right? So maybe this is the reason why we don't do multi-class classification in logarithmic time. It's not consistent. We don't actually get the right answer. But it turns out this can be fixed. There's a simple fix. The simple fix is, instead of learning 1 versus 2 and 3 first, we learn 2 versus 3 first. So if you learn 2 versus 3 first, then 2 and 3 each have probability 0.3. It doesn't really matter which one you choose. You choose one of them. And then we have a classifier here. So we're going to keep all the examples that the classifier agrees with for training up here. So instead of training on all the 2s and 3s, we train on either the 2s or the 3s, depending on what our classifier predicts. And now the probability of label 1 is going to be 0.4, and the probability of probability of the winner of 2 and 3 is going to be 0.3. So it's 0.4 versus 0.3, and that means that the classifier that we learn at the root is going to prefer label 1. Okay, so this is the core essence of why you can actually, it says that you can, in fact, learn statistically in a logarithmic time predictor. And you can prove a regret bound. You can prove that the average binary regret over the nodes that you learn times the depth of the tree bounds the multi-class regret. So this is a notion of regret which is relatively strong. I'm comparing myself to a baseline which is essentially called the Bayes optimal classifier. It's the one that you get if you don't have any constraints on representation. Yeah?
This is a very sort of maybe off the cuff comment, but is that log case something more like an entropy? Is this, would you expect to see some kind of entropy of the class distribution?
It's not really an entropy. It's more a depth of the tree. So if you look at the proof, what happens is you end up adding up the regrets at each level in the tree.
But it's averaged over the likelihood of seeing that item, right? So it's like some kind of average depth over the probability.
Yeah. So if you do a more refined proof, you'll have an average depth. That's true. So that is very related to entropy, but not exactly the same. Okay, so now maybe the reason that we don't use logarithmic time prediction is because of that log k. right? I mean, we don't want to have a regret be multiplied by log k. That's a bad thing. Maybe trees just inherently have a larger error rate because you have multiple opportunities to fail as you walk down the tree. Okay, so can you make it more robust? That's the basic question. So this is a binary tree on 8 labels. It has one winner. And now the green is another binary tree on 8 labels, which has a winner. And then the blue is another binary tree on 8 labels, which has a winner. Okay, so let's go back. So if I want to make things robust, I need to be doing some sort of error correction. That's pretty clear. I told you that depth is sort of the critical parameter here. What is the depth required in order to do 3 binary trees on 8 labels? You might think that it's 3 times log base 2 of 8, right? So that'd be 9. But if you look here, it's actually 1, 2, 3, 4, 5, 6, 7. So I shaved off 2. And this construction is much more impressive if you start drawing much larger graphs. But then, of course, it's much harder to read. So in general, it turns out that it's possible to have log k distinct tournaments on k things with depth order log k. That's kind of cool. And that means that you can prove something. You can prove that if you have a log k correcting tournament, the multi-class regret will be bounded by the average binary regret times about 5.5. So this is a constant rather than a log. Okay, so I didn't quite finish what happened. So you have 3 winners here. But once you've reduced the set of k possibilities to a set of 3 possibilities, or more generally log k possibilities, then you can do something much more robust and hardcore on that last log k, and then everything still works out. Okay, so this is interesting. I haven't seen it be useful yet, except in ICML 2012, we were running the Best Paper Award, and the area chairs were the nodes. Right? And that worked pretty well. So it's a nice way to kind of distribute computation across, distribute decisions across a bunch of different people in a robust manner. Okay, so this says that you can have things that are robust. So we can be both statistically sound and we can be robust. And now the question is, why aren't we doing things in logarithmic time? So one answer might be that programming this is a little bit annoying, but in fact, I did program this up. It's in Bopal-Wabbit. You can experiment with it. People still aren't using it that much, and why not? This kind of thing's handy, but you know, I'm trying to solve machine learning, not best paper award picking. Okay. There's another problem which comes up, which has to do with our notion of regret. We're looking here at a pretty hardcore notion of regret. It's regret with respect to the representation independent best classifier. And we're looking at regret here with respect to a representation independent multi-class classifier. Representation independent is not actually what we often work with. Often we work with a constrained representation, like linear prediction or something like that. And when you're working with a linear prediction, there can be classifications which just don't work that well. So think about, suppose you're going to try to do digit recognition, right? So you could split 4 labels in 2 different ways. You could have 1 and 7 versus 3 and 8, or 1 and 8 versus 3 and 7. Which one's better? So So 1 kind of looks like 7, 3 kind of looks like 8, 1 doesn't look like 8, 3 doesn't look like 7. You can see how there's some sort of similarity preserved here, but not there. So is it better to have a split? But it's not clear, not that obvious which is going to be best, because maybe you want to have an easy decision at the top, and then you want to have a hard decision between 1 and 7. Or maybe you want to have a hard decision at the top, and then an easy decision between 1 and 8. Which do you actually prefer? So this is basically settled. This is Bingio, Weston, and Granger. Had a paper where they showed empirically that it's just better to confuse labels near the leaves, better to deal with confused predictions near the leaves than near the root. And the intuition for this is that the root of a tree is highly constrained. And that means that it's actually quite hard for it to predict well. And so you want to relieve the constraint at the root, while at a node just above the leaves, it's only deciding between two things. There's not that much of a constraint. Even if it's a pretty hard problem, it can sort of nail that pretty well. Okay, so now there's a bit of an issue because of the question you asked earlier. Are we trying to do an order log k training time or an order k training time? If you're trying to figure out which classes are easily confused or which sets of classes are easily confused, you could easily run up to even an order 2 to the k running time if you wanted to look at all partitions, right? And an order 2 to the k would be disastrous, and order k would be disastrous. So we really want to get order log k training time. And now the question is, how do we even deal with this confusion problem when we want an order log k prediction training time? Okay, so we need to think a little bit about what we actually are trying to do, because at a node in the tree, a node in a tree or a node in a DAG, we're not trying to solve a full multi-class problem. We're just trying to solve a piece of the problem, and we want a piece of a problem with a property that it will compose to allow us to solve the overall problem, and that it's relatively tractable, right? So this is a definition of the partitioning problem. So what is partitioning? Partitioning is when you have a bunch of different labels, and now you want to partition between one set of labels and another set of labels. Right? But you don't know what that partition is in advance. Okay, so that's kind of a strange thing. For a long time, I thought that this was just fundamentally different from classification. So here's one way to try to formalize what partitioning means. You can say, look, I have a partitioner, H, and I'm going to measure the quality of this by looking at the expectation over my data set of, okay, so this is the probability that my partitioner predicts label 1. This is the probability that my partitioner predicts label 1, given that that the example comes from, has a particular label. Okay, so if this number is the same as this number, so everything is kind of split randomly, essentially, then this is 0. So that's not good. We're trying to maximize this value. A good partitioner is one which is going to maximize this value. So what we want is all of the labels, all of the examples of a particular class go to either one side or the other. So we want this number to be either 0 or 1, and we want this number to be 0.5. That would be a really good outcome. Okay, so this is a strange optimization because this is very inherently non-convex. So if your hypothesis class is symmetric, which essentially everything that we work with is, then you have a solution like this and like that, and they each have the same quality. But the average of these two solutions may have a very poor quality. In fact, it has value 0. Okay, so that's kind of disturbing. Can we actually optimize this? That's an important question. And more importantly, and also, does this actually work? If we optimize this, do we actually end up getting a good solution? Okay, so because we thought about the filter trees, it's natural to think about a bottom-up approach to trying to construct these partitions, right? It turns out that doesn't work. We don't know how to construct things bottom up, and in fact, it seems very difficult. So suppose we're looking at linear representation, so we're representation constrained. We're doing linear representations, and we want to build a tree on these 3 labels, right? And let's suppose these labels are, in fact, on a line, just as they're represented here. And suppose that we choose 1 and 3, and we build a predictor. So this is easy. We can predict 1 versus 3 very well. And then we build another predictor, 2 versus 1 versus 3. And that's not going to work very well, because you can't linearly separate between 2 and 1 or 3. Okay, so it's just like it's a you-lose type situation. So it seems like bottom-up construction is just not feasible. At least I don't see how to make bottom-up actually work. Okay, so that says that we need to perhaps build our partitions top-down. And now there's kind of a question about whether or not the partitions that we build top-down actually will compose to give us a good solution, right? Every individual node is we're trying to solve a partitioning problem. And we want to know that if we solve a bunch of partitioning problems going down some tree or some DAG, do we end up with a good solution? And the answer ends up being yes. What you can prove is essentially a boosting statement. You can say that if I manage to partition well at each node, then after I do something like this many splits, the multiclass error rate that I'll get is less than epsilon. Okay, so this seems like a lot. It's important to take a log when thinking about this number. Gamma here is how well you're doing your splits. And now there's 2 things about this theorem which are worth pointing out. There are other boosting statements for tree construction. This is a similar statement to those with 2 kind of caveats. One of them is we have a for all y here, which is bad. That's strengthening the quantifiers for the if part. So we're supposing that we actually managed to decide relatively well for each individual class. And then we have a log k. And the log k is pretty cool, because you would like the depth of the tree to be logarithmic in the number of classes, which is not achieved by all the other multiclass boosting statements that I know about. Okay, so now there's the question about how we actually find these partitions. So you could, of course, use guess and check, right? I mean, you could just guess a partition, train, evaluate, guess, check, over and over again. But it's much more tempting to try to make some sort of more efficient algorithm, because the problem that we're concerned with is efficiency. And if you try to look at efficient optimization algorithms, then often you're looking at online algorithms. And now what I'm going to do is I'm going to twist the problem a little bit. I'm essentially going to use a ramp law. So what I mean here is I'm going to be thinking about linear prediction. And what I'm going to be thinking about here is something which has a value as small as -1 and as large as 1. And between those values, it's going to be w dot x. Right? So if you take a max with -1 and a min with 1. So this is a continuous relaxation of the optimization criterion, the partition definition that I was talking about before. Okay, so now we can try to create an algorithm. And how are we going to do this? So we're going to keep track of, so we have an expectation for all of our examples. We have an expectation conditioned on y. So those are going to be start out at value 0 and value 0. And we're going to keep track of the numbers so we can get the expectations right. And now for each example, we're going to run through. And if one side is preferred, then we're going to set a binary label of -1, and otherwise we're going to set a binary label to 1. And then we update w using a binary labeled example. So when I started out on this, I was thinking that this problem of finding a good partition is not really very relatable to classification. It seemed like it was just kind of a different problem. But here what I'm doing is I'm essentially reducing the partitioning problem to a binary classification problem. So I can reuse my existing binary classification algorithms. Okay, so then we do some bookkeeping. We keep track of the count, and we change our expectation to match the actual true expectation. And then we apply this recursively to every node in a tree to construct a tree. So now the question is, does this work? So here's a problem. This is not a real problem. This is kind of an acid test, right? So you have 100 classes, which are arranged in a two-dimensional grid, and you just unleash the algorithm on it, right? So each of these classes is drawn from a Gaussian. These Gaussians are imperfectly but nearly separated, and you just go. So if you run this algorithm on that data set, we got a test error rate of very small, right? So something is going right here. If we were doing a bottom-up construction, our error rate would be near 1, and we would be losing. Since we're doing the top-down, we're actually succeeding fairly well. Okay, so another question you could ask is, how good is the partition that we're creating? If you look in particular at the root of a tree, it's essentially a binary classification problem there, which is get everything to the left on the left and everything to the right on the right. So if you look at the partition that we create, it has a binary classification error of 0.1253 on MNIST, which is 10 classes. And if you look at random partitions, then they don't do much better. So the average error rate is much higher, and there's some standard deviation, which occasionally does as well. Then if you look at RCB1, which has 100 classes, about 100 classes, there's an even bigger gap. So this online partition construction process that we're using is actually fairly effective. Okay, so now if we compare with 1 against all on these data sets, it seems like it works, but it's one of these trade-off things. We're getting performance which is not as good in terms of test error, but which of course is radically better in terms of computation. So I think what's biting us there is essentially the log k, right? There's still log k ways to go wrong, and we need to actually fix that to do better. Okay, so I'm done. There's a workshop at NIPS on this subject. There's a lot of other people who have become interested in this kind of problem. There's a bunch of other issues that I didn't really discuss. One thing which comes up is the state is not logarithmic for the kinds of algorithms that I was talking about. You'd really like the state to be logarithmic as well. And then you also want to be able to deal with label-dependent features in many natural settings. Other questions?